squared down or slash towards the center of Earth, or whatever object, if you're comparing the gravitational force to two objects, but usually here, and I said acceleration, but I really mean magnitude of the acceleration, meaning the size of it, because g is a constant. It doesn't have a direction to it. G, 9.8 meters per second squared. You'll see acceleration due to gravity. If you flip to the backside, you'll also see it's called the gravitational field strength, aka gravitational field strength. So some things like mass is constant wherever you go. An object's mass will not change. So let's say you have a 50 kilogram astronaut. Here on Earth, that astronaut weighs 50 kilograms times 9.8 meters per second squared, which is about 490 newtons. But on the moon, that astronaut is going to weigh less. But the astronaut's mass is 50 kilograms still, because that's constant. But the weight might be instead, let's say, 80 newtons. And then you can be like, oh, what's the gravitational field strength, or the acceleration due to gravity? Well, F sub g over m is going to get you 80 newtons divided by 50 kilograms, or 1.6 meters per second squared, which is close to, but not exactly, the acceleration of objects on the moon. Meaning, if you drop an object, all dropped objects fall at this rate. That is the acceleration of all dropped objects. But that does not mean that that is the acceleration of all objects. A box on Earth's surface might have a weight of, meaning it might have mg of 100 newtons, and that means that the mass is about 10 kilograms. I'm rounding just a little bit. 10 times 9.8 is 98. I just rounded it up to 100. But that doesn't mean the acceleration is equal to it, because it probably has an upward normal force as well, so it probably has an acceleration equal to 0 meters per second squared. So don't get 9.8 mixed up. It doesn't necessarily mean the acceleration of an object. It doesn't mean that is the force on an object. It just means that you can use that to find the object's weight. So getting into projectiles, all dropped objects fall at the same rate, which is to say the same acceleration. And there's an if you ignore air resistance, or it's often called air friction. Similar to friction, but it's got a different kind of mathematical properties to it, let's just say. Because air friction or air resistance increases as you speed up, whereas regular friction does not. So let's say you reach terminal velocity, meaning you include air resistance. You've got an air force up, you've got your object's weight down. That means your net force is equal to 0, your acceleration is equal to 0. You are not speeding up. You're moving at a constant speed. So if you drop an object, it eventually will reach a constant speed because of air. But without air, your free body diagram looks like this. You might just have a force down. Let's call that force 500 newtons for now. And this is true for a dropped object, but also an object thrown upwards, or all projectiles. And projectiles, I mean, a dropped object is basically just a limited type of projectile. Anything that's going in a parabolic arc, whatever it is going to be a projectile if it's defined as having only the force of gravity acting on it, if you are ignoring air resistance. So all projectiles will have the same free body diagram. So that means that they will always have the same acceleration. So A equals negative 9.8 meters per second squared on Earth. And so let's say you drop an object. That tells you your initial velocity is 0 meters per second. So at t equals 1 second, your speed has changed by 9.8 downwards, so you're now going at negative 9.8 meters per second. At 2 seconds, your velocity is now 19.6 meters per second. 3 seconds, your velocity is now negative 29.4, etc., etc. So every second you are speeding up. If you throw an object upwards, for example, and your initial velocity is, let's say, 30 meters per second up, well, at t equals 1 second, your velocity is now, and I'm going to make an assumption here. Let's just say a is equal to negative 10 meters per second squared, just to simplify it. So now, normally we'd be going by 9.8, but let's go to 10. Now your velocity is 20. At 2 seconds, your velocity is 10. 3 seconds, your velocity is 0. And this is going to be essentially your maximum height, because as soon as your velocity goes from positive to negative, a second later, negative velocity, negative 10, means you're moving downwards. Five seconds, velocity is negative 20. 6 seconds, velocity is negative 30. And this is where you're going to hit if you're throwing it to the same elevation. When your initial velocity equals your final velocity, that is the point at which you come back to where you started. There we go. You're back to your starting point. And this is the same for projectiles. So you could, for example, take a projectile and give it an initial velocity and an angle. But let's say we don't even, honestly, we don't even care about the horizontal motion, v sub x. We just care about the vertical motion. If v sub y, let's just say it's a 3, 4, 5 triangle. If v sub y is equal to 30 meters a second, v sub x may be 40. It doesn't matter what v sub x is. It doesn't affect the time that you're in the air. It affects the range, but not the time. And this would be 50. Well, it's still going to be, after 1 second, v sub y is going to be 20. 2 seconds, 10. 3 seconds, you reach your maximum height. V is 0. 4 seconds, this is going downwards now. 5 seconds, it's at negative 20. 6 seconds, you hit the ground, and you're back to your starting point. Having said that, keep in mind that these dimensions need to be separated. We need to do vertical and horizontal separately. So let's say, for example, it takes 6 seconds to hit, which is we get from the numbers, and you can get that from kinematics too. Well, how far does it travel horizontally? Then we need to do with the horizontal speed. Horizontally, it goes distance is velocity times time. It's constant speed because your acceleration is 0 meters per second squared. So it has gone 40 meters per second times 6 seconds. So 240 meters. And so to put that in a more formalized way, let's look at projectiles. Projectiles, there we go. So we know that projectiles are going to basically, there's a couple different ways to talk about them, but let's just always separate the vertical and horizontal motion. And often, you don't even need to do both. Do one at a time. So vertically, your acceleration is negative 9.8 meters per second squared. Horizontally, your acceleration is 0 meters per second squared. And this is true for all launches. That's the most important thing. And if it's that, if this is constant speed, then you can d equals vt. But here you're going to need to use kinematics equations like, but not limited to, vit plus 1/2 at squared. So let's do more of this in a second. I'm going to pause.